For the most part, I've tried to stay away from physics subjects in my videos that I do. And that's because the field of physics can have a lot of things that are complicated, counterintuitive. And in the fields of physics and engineering, they require undergraduate degrees and graduate degrees. So for the most part, I never wanted to wade into water that deep. Instead, I preferred to just stick with simple math equations, driving equations. I move variables around, I insert one equation into another, combine a bunch of equations, and in the end I get a result that's unequivocal and inarguable. So for the most part, I've stayed away from theory, which is what a lot of the physics is, because it's complicated and I have difficulty proving it for the most part. At any rate, I got curious about some things, so this is one thing I got curious about. When something starts spinning around, like say those rides at an amusement park or a governor on an engine, then if you have these swing arms here, these arms will swing out. And I was curious what causes that. I'm going to show two approaches here. One is intuitive, the other one is just with some vectors, which is still sort of intuitive. On this particular subject, I couldn't find any answers here. All I could get was the reason that arms swing out when they're spinning is because of centripetal force, and that was it. And that's actually not an explanation. You could easily just say that the arms swing out because it spins really fast. So that doesn't tell us anything. So here's what I came up with. I think it all makes sense, and I'm just following the rules of physics and vectors, so this is what I got. First off, a couple of nuances. In this situation, we're looking across right here, so we're level with the spinning thing. The arms will not completely reach horizontal because we'll always have gravity pulling down. But if you're out in space and there's no gravity, I assume that these arms would swing up and be horizontal. Next up, okay, so this was looking straight across, and then so we're level with it. Here we're looking down on the swing arm, so it's swinging around like this. We're looking down on it. We have a mass attached to either a rope or a solid stick, beam, whatever you want to call it, pole. The way gravity will always push down on the masses here, I'm assuming that if something is swinging around in an atmosphere, you'll have the drag force pushing back on it, so that arm will never actually reach completely 180 degrees. Those are my assumptions, and like I said, I couldn't find any information on this, at least when I searched for it, so this is just what I came up with. So here's an intuitive approach. Say this is like the Fulton Skyhook that they used back in the Cold War, where there's a person here that's represented by a mast. They have a helium balloon that goes up with a big rope, and then an airplane comes by and catches that rope and yanks that person up in the air. This is one explanation as to why things will swing up if you accelerate them. If you just look at your force vector, we have our arrow here representing an airplane or something. We have the rope right here that's also the force vector pointing up. So thus, this thing is going to be accelerated up with a great amount of force if it's a plane going by really fast. This is also on the subject of why the classic trope, or those old scenes from cartoons and movies, show a person hanging onto the back of a vehicle and flapping in the wind as they get dragged behind. That wouldn't work because gravity is always pulling them down. So once they get that initial acceleration, that'll pop them up, but unless that vehicle continues to accelerate, then they no longer have an acceleration pulling them up and they're going to fall. And that's simply because of the acceleration from gravity. So mass times acceleration equals the force. That will provide a downward force. Thus, the acceleration of this person always needs to be greater than gravity. And it always needs to be pointed up, so that way they'll always fly up. But here's an analogy on how we could keep this ball or this mass up in the air if a plane comes by and pulls it up. By the way, I'm going to ignore air resistance, because then things could have some sort of an aerodynamic lift to them, and then the air could keep them up. So let's just pretend it's happening in a vacuum. So a plane comes by, or a spaceship, whatever, flies by and yanks this up, so now it's behind it. This object that's pulling this thing and holding it in the air, this flying thing needs to continually accelerate. But if it continues to accelerate in a straight line, it'll eventually reach light speed, and that's just not possible. So what you can do is continue to accelerate this mass at different angles. So once this first spaceship comes by and flies past and yanks it up in the air, but then immediately lets go of that rope once it's this mass is up and level. But then as soon as it yanks this mass up and it's level, it lets go of that rope. But a fraction of a second later, before this mass has a chance to drop, another spaceship comes by at a different angle, say 5 degrees to the left, and yanks it in a different direction. And then immediately lets go of the rope, and then another one comes by and yanks it in a different direction, say another 5 degrees to the left. So it keeps getting accelerated at different angles, and that's what keeps it up in the air. All right, that's the intuitive approach. On the next page, I'll show a vector approach. All right, first off, we have a swing arm right here. We're looking straight down on the image. So the ground is underneath or behind this swing arm. We have a swing arm right here that swings around in a circle. And then attached to the end of this swing arm could either be a rope or a connecting rod that attaches to another mass out here. And we could say this is a rigid connecting rod, but if it's attached to the swing arm, it'll need to be attached to the swing arm by like a rope or something, so that way it can spin and rotate in all directions, left, right, back and forth, whatever. The initial stage here will require an energy input, so we'll have to crank up the electric motors to rotate this swing arm and start swinging it around. This swing arm right here, right here, as it moves and swings in a circle, it will pull on this connecting rod right here, or this rope. That'll be the centripetal force, F sub Cp, pulling this mass in that direction. The velocity of this mass right here will be at a right angle to the force. So the velocity is pointing off in this direction. This mass can't have a velocity inward because then you'd have slack on your rope or this connecting rod to be pushing against it. And this mass cannot have a velocity outward because it's being tethered by either the connecting rod or this rope right here. Thus, its velocity will have to be at a right angle. So we can draw our theta right here. Since we have a force right here pulling up, then this vector right here on the bottom would be the sine of theta, and that will represent the forward force of this object. As this swing arm comes in and gets closer and closer to 180 degrees so that it's forming just a straight line, the sine of theta will get smaller and smaller. Thus, we'll have a smaller and smaller force pulling this object out to horizontal, or I should say at a straight line. And from what I can tell, this is why, under the influence of gravity, the mass will always be pulled down a little bit, because the sine of theta will be much smaller, so it won't be able to overcome that last little bit of distance to become completely horizontal if either gravity is pulling it down or there's the force of air drag pushing it back. But if this mass is way out here, you're going to have a very large sine of theta, which means you're going to have a very large force pulling it in, or pulling it out to a straight line here, and thus that force can overcome gravity and air drag. I think the most important concept here is if you add a force to your velocity, you're going to get an increased velocity. So we have a velocity in this direction, we have a force in that direction. When we combine them, that will cause this mass to swing out and get closer to a straight line or 0 degrees right here, or you could say 180 degrees. And again, we're putting energy into the system. That's what's pulling this mass out to 180 degrees. So now that we have our mass in a straight line with the swing arm, we can turn off our electric motors. We do not need energy anymore if we pretend that this is a friction-free environment. And that also includes friction from air, so there will not be any drag force of this mass passing through the air. The mass will have a velocity that's tangential it'll have a velocity with a direction that's tangential to the outer circle. It'll still have a constant inward force of centripetal force or centripetal force. We no longer need to put energy into the system if there's nothing slowing it down. We will have a continuous acceleration without increased velocity, and that's what will keep this object up in the air. I think this is an interesting concept. I've heard this ever since I was in school, how you can have a continuous acceleration but no increase in velocity. And that's because the mass here is continually being accelerated into a circle, so its velocity will stay constant. So I just said here, no energy is needed if there's nothing slowing it down, and we will have continuous acceleration without an increase in velocity, and so no increased velocity. Here's an analogy also. Imagine rolling a marble across a hard floor, and that marble reaches a banked curve. So let's just say maybe this mass right here is rolling across a hard floor. Here's a bank curve. We're looking down on this, so this curve is going to curve the marble to the left. That marble will want to rise up that bank curve as it goes around the corner. And that lift will be from the centripetal force. And we have the equation mv squared over r equals the centripetal force. And that's how we calculate the angle of our banked curve. So a marble going around a banked curve is the same situation as this mass swinging around on a swing arm. The marble will not increase its velocity by going around the curve, even though it will be accelerated inward. But if it's a friction-free environment, whatever velocity the marble has as it enters the curve will be the same velocity as it exits the curve. This actually brings up a tangential thought or a tangential myth I've heard of ever since I was a kid. I've always heard that roller coasters would go around a banked curve because that increases the roller coaster's velocity. So that's another myth we can debunk, in addition to the one of the cartoon character hanging onto a vehicle and flapping around in the wind as it's lifted up in the air. If you want, you can see my other videos on the bank curve and how to calculate that angle.